Okay, having done this, now Friedel-Crafts reaction was substitution electrophilic reaction. Why? Because it occurred at double bond somewhere here, which was electron rich. Alright, so that's what happened. Now we are talking of substitution nucleophilic reaction of haloarenes. What would that be? That would be here we are generated carb cation here. In this case, we would generate carb cation over here. Alright, so for this sort of reaction, what you need to do is you need to generate carb cation over here. Whereas in this case, it was what? It was the double bond which was attacking the carb cation. So this was electrophilic reaction, and this is nucleophilic reaction. This was electrophilic reaction, and this is nucleophilic reaction that we are talking about. So we need to generate carb cation over here. Alright, so if we need to generate carb cation over here, then this Cl has to come out as Cl minus. Alright, is it feasible? It is not feasible, owing to 1, 2, 3 reasons that I'm going to explain right now. Alright, now first reason is, now check out over here, this lone pair of electron shifts over here, forms double bond characteristic, and this double bond characteristic is stabilized by what? By this shifting here, this shifting here, then this shifting here, this shifting here, this shifting here, and this shifting here, and again this shifting back to this space. So what was all this? Resonance structure. So these resonance structures are stabilizing C double bond Cl. Bond length is 169 picometer, whereas if you check out single bond length of methyl chloride CCl, that is 178 picometer, whereas this is 169 picometer double bond characteristic. So how can you break double bond, right? So no, it cannot go out as Cl minus, it cannot go out as, if I draw it over here, Cl, it has to go like this, right? It cannot go out as Cl minus and generate carb cation, right? It cannot go. Why? Because of this double bond characteristic of CCl bond. Fine, that's the aspect number 1. So resonance effect does not let the SN reaction to occur, substitution nucleophilic reaction to occur. Fine. Okay, let's go to next part. Now in next part, what we have is, we are talking in terms of SN2 mechanism. In case of SN2 mechanism, what did we study? SN2 mechanism, we saw that in transition state, this was leaving group, this was leaving group, and this was incoming group. Incoming group, leaving group, we had making and breaking, I would put it as making and breaking. Partly making bond was there and partly breaking bond was there. Both were there. So for that, what do you require? For that, you require steric factor to be in favor. Alright, but here we have got big aromatic ring here attached. So there is no scope of backward effect because of this big aromatic ring which is available. So backside attack ruled out. Why? Owing to blocking of aromatic ring from backside. It's all like that, right? Aromatic ring block. So SN2 is ruled out. Alright, okay, so that also gone. Now let's think in terms of SN1. For SN1, suppose here already we ruled out the possibility of generation of carb cation. We ruled out this. Suppose if it happens, carb cation happens here at aromatic ring, would it be stabilized? Would it be stabilized by resonance structure? No, it is not stabilized by resonance structure, right? It is not stabilized by resonance structure. Stabilized in the sense, would it have those many resonance structures if we just have C plus over here? Just by having C plus here, you cannot have resonance structures. You are finding how the shifting occurs. There's nothing to shift like that. Alright, so no resonance occurs. So no stabilization of resonance. Therefore, SN1 also ruled out. Alright, and so these two are also gone. Finally, we also have this third one, which is this carbon. Check it out. This carbon has got 1, 2 and 3 groups attached. So it's sp2 hybridized state. So sp2 hybridized state ruled out for generation of carb cation. SN1 ruled out, SN2 ruled out, and resonance effect ruled out, because resonance effect also ruled out the generation of carb cation because it has not double bond, right? SN2 ruled out because of bulky aromatic group blocking the backside attack. Alright. SN1 ruled out because no stabilization of positive charge. Alright. Carb cation. And finally, it's sp2 hybridized state. Very difficult to break. So owing to this reason, it's very difficult for us to carry out substitution nucleophilic reaction, that is substituting this Cl by any other OH minus, NO2 minus, or any such groups. Alright, so such nucleophilic is not possible. So is it not possible for us to do that? Yes, it would be possible, provided we activate this. Activate in the sense, this bond has to be shifted towards the aromatic ring, so that Cl goes out. Alright, so how does that happen? That happens by introducing some highly electron withdrawing group. Alright, so let's read it out. For nucleophilic substitution reaction to occur, ring needs to be activated by strong electron withdrawing like NO2 group at ortho and para positions. So let's try and understand how can we make impossible possible. Alright, you know IMPOSSIBLE. Just remove IM, it's possible. Nothing is impossible. Alright, impossible also says I am possible. So let's see how we make impossible possible. Electron withdrawing group. So we apply 1 electron withdrawing group here. Alright, we apply 2 electron withdrawing group here. We apply 3 electron withdrawing group over here. And let's try and understand what's the effect of it. Now, here the situation was 1 nitro group at para position, sodium hydroxide, temperature. That's in first step. In second step, now since we have used sodium hydroxide, so this would be in Na form, sodium salt, alright, of paranitrophenol, sodium salt of it. Alright, so we have got to get phenol. So sodium has to be acid. So Na salt has to be acidified with acid. That's why we use acidified solution. So that's why we use acid. Alright. Okay. So in step 2, here since we have used sodium hydroxide, so we would get Na salt. So in order to remove Na salt, we have got to acidify. So step 2. Similarly here also, same thing we do. But here it is, I'll come to this part at the end. Now so here the reaction impossible gets possible by this condition, by applying 1 nitro group here. Alright. As soon as we apply nitro group here, we get paranitrophenol. Alright. But at temperature 433 Kelvin. Alright. Now here we apply 2 nitro groups, electron withdrawing groups, strong electron withdrawing groups in ortho and para position. Check out the temperature. Instantly there's a droppage of 30 Kelvin. Alright. So we get, so it has also to be acidified, because here also we have used sodium hydroxide, so we would be getting sodium salt. In order to remove sodium salt, we have got to acidify it to get it H. Suppose I use HCl, so I'll get NaCl out, and this would be phenol. Alright, dinitrophenol. Fine. Now comes the final concluding part, where we are using 3 nitro groups, ortho, para. We don't require this, we don't require this, we don't require this either. So since we are not using sodium hydroxide, so we don't even have to acidify. So step simplified. So just warm and water hydrolysis gives you phenol, right? Which phenol? Trinitrophenol. Alright, now see how we made impossible possible by introducing strong electron withdrawing groups. Alright, so something extra I would like to talk about this. Now this is known as picric acid. Picric acid is used in explosives, it's used in dyes, it's also used in leather industries. It has lots of application, picric acid. Okay, it's all very clear, quite interesting. Okay, study well.